Okay, so we just did neutralization reactions of strong acids and strong bases. The next page is all about weak acids, but we're going to skip that for now because the neutralization reaction works the same way. We just end up with, well, I guess we're not going to skip it. So we've just finished up looking at the neutralization reactions for strong acids and strong bases. The next page would have you do weak acid neutralization. Let's go over that really quickly, but we're not going to do this page. We're actually going to skip this and move on to the next concept because the neutralization reactions themselves work very similarly. So when I say that, let's look at an example. Let's say HF being neutralized by, let me just get my pens ready here, being neutralized by, and let's just use our classic example, NaOH. It's pretty much the simplest base that we could use. So when that neutralizes, it's still going to have the exact same reaction. So I'm still going to have H, let's use the right colors here. I'm still going to have H, OH, plus NaF. And that's still going to be aqueous. So we should be able to see this neutralization reaction occurs the exact same way. The difference in a weak acid and a strong acid being neutralized is that this aqueous solution right here, this NaF, remember why the weak acid worked the way it did. This NaF, let's look at that. NaF is really going to break up into its two ions. Those are going to be floating around. Those are going to be an aqueous solution. So then I'm going to have F minus. Now what's going to happen here? Well, this is still going to interact with the water. So this is still going to interact with the H2O. And that H2O is still going to naturally dissociate. So we've got H plus and OH minus, right? It naturally does that. But remember, the reason hydrofluoric acid was a weak acid is because this fluorine was, we could say it's more hungry for those hydronium ions than the hydroxide is. So this fluorine is still going to snatch some of these extra protons up and will have an excess of hydroxide. So just because these two are sitting in water, what really happens here is we end up with Na plus some HF still sitting in that solution. Now this isn't the acidic HF, this is still a neutralized compound. There's no more hydroxide for this to react with. This original amount has been neutralized. But some of this is just going to get pulled away naturally, and then it's going to kind of go back into that equivalence reaction that we talked about before, where it's going to go one side is HF, the other side is breaking back up into H plus, F minus, things like that, back and forth, but it's still going to be overall neutralized. So if we look at it that way, then what we really get, let me make that a plus. But then what we really get is we have these leftover OH that are just hanging out, that aren't able to recombine with that hydrogen to form H2O again. And so overall, when we have a weak acid neutralization, we end up with a larger concentration of hydroxide, which means our pH is higher than 7. When we did a strong acid and strong base, they would completely neutralize each other, and our pH would be 7. It would be completely neutral. But when we have a weak acid and weak base, that pH has to be higher when it's neutralized. And that makes some complications in other areas. So I just wanted to show you that. We're not actually going to go through and do any of the stoichiometry with that because it really does work the same way. You would end up just doing this solution. The only change, the only way that this actually becomes a little more complicated is when we factor in how to figure out the pH after the neutralization, where you actually have to go through and look at this leftover here. We're not going to deal with it.